Let's take a couple of minutes here and talk about pointers and arrays. Pointers and arrays, and remember that an array is an assembly of all the same type of data, all characters, all integers, all longs, all the time. No other types can get slipped in there when you make up an array. Here we have an example of a character array that is 12 positions long, 0 through 11, down here, 12 characters. Right next to it, we're also going to create, this is a standard C statement, an expression. We make a character A of 12, comma, a pointer called P, and this will be a character pointer, it has an asterisk there, and our initialization sets P equal to the address of A sub 0, which is this first byte right here. Now we could have just as easily said in this definition that P is equal to A and left off the address of sub 0, because that's what A is. When we created an array, A references the address of element 0, of the 0th element, the first element. Then, after this statement is performed, these are equivalent. Contents of P is the same as A sub 0, which is an H. Contents of P plus 1 is the same as A plus 1. And really in the compiler, when you use A plus 1, it is changed into contents of a pointer plus 1. These brackets go away before the compiler gets a hold of the code. So this is what's really happening in here. We have to use the parentheses because of the relationship of the asterisk and the addition so that we get the right form here, that we get what we wanted. We don't take the value out of here and add 1 to it. We want to add 1 to the pointer and then dereference it, get the contents of the pointer incremented by 1. So we can use this, and obviously we can use variables and other things in here, not just these literal numbers, to work our way up and down an array. And it is legal if you set P up here someplace to use negative numbers and work your way backward down the array. So these are array subscripts down here, and these are pointers with integers added to them to also cause them to subscript the array, to go up and down the array. This will be faster in the code because the code is able to optimize itself to make better decisions if you use this sort of subscript. But it's just as good. We're working on pretty fast machines now, so it's okay to use bracket 0 bracket or bracket with a variable in there to work your way up and down an array. So pointers and arrays are tightly coupled together because a pointer is doing the same thing as an array name and subscript. And any array subscript operation like this, as we say, can be performed with pointers more quickly, but it can be a little bit harder to read. Now, one thing you cannot do is you cannot set this value, A. You can't change it because it is actually in the code. It's a constant, and it is a constant that refers to the address of this 0th element. So if you want to deal with the address of it, you need to make a fresh pointer and set the value of this address into that pointer so that you can dereference it and work with it as a pointer. But you can't go setting that A to something else because that would point it off of the memory, off into space someplace, and this thing would be sitting there, this sequence of characters would be sitting alone in memory with no way of finding it and getting back to it. So that's the coupling between pointers and arrays. We already touched on this, pointer arrays and pointers to pointers, but I want to repeat it again because I want you to make sure that you understand that you can do these kinds of things. And it's quite powerful, and you may find a situation in a program, you certainly will if you're dealing with database records and lots of records of similar data that you need to compare to one another, and you don't want to move all of the data all the time. I mean, that's the most inefficient way to go. What we're going to do is we're going to talk about a pointer as just another variable. That's all it is. A pointer is a variable that can contain the address of some place in memory. We already know that. Well, since a pointer is just another variable, it can also itself be manipulated. We saw how we do pointer math. We can add numbers to pointers, we can subtract one pointer from another, and so on. But one of the things we haven't looked at is radically changing the value of a pointer, even swapping the addresses between multiple pointers. For example, if we have an array of pointers, think of it as a large group of pointers, each of them pointing to an element or an individual row in a database. The columns can be compared, I want to say, and then the pointers swapped with one another rather than swapping all of the data values. That's an easy way to do a sort. You sort the pointers into the order that you want and then run down through the index list of pointers and retrieve the data in the correct order that is necessary for your application. Let's take a look at a piece of code here. Not a piece of code, but just a table. Here's 3 database records, and there are addresses on the left column, and on the right column are the database records. Well, all you have to do is go through and compare, like I said, the various columns in the database records, whether it's a state or a last name, first name, a price of something, whatever you're looking for, and then when you find 2 that are out of sequence, you switch the contents of the addresses in the array there on the left side. Those are all pointer arrays. So by switching those values around, you can actually resort the database table without sorting the database table. If you're familiar with databases, that's just an index. That's all it is. But we're going to create those indexes in memory using pointers, arrays, and then pointers to pointers, because you can use another pointer to sequence down through this table one at a time, incrementing it, and since it is created as a pointer to a pointer, it will increment by the appropriate number of bytes to go from one pointer to the next one. We've so far discussed single-dimension arrays. Now we need to talk about multi-dimensional arrays. A spreadsheet, like in Excel, that is a 2-dimensional array of rows and columns, or elements in a database. If you think about a single-dimension array, is similar to a series of alphabet blocks set along in a row. They can be integers with numbers on them. They can be letters or a character array. So each of the blocks would have a single character on it, and then null at the end if it's going to be a string. They could be floats or doubles or any other native type that we have in the language, but there's just one string of them. That's a single dimension array, and we sequence through the array name with brackets at the end, 0 through whatever the length of the array happens to be. A 2-dimension array, we already said, is like a spreadsheet, or can be thought of as a stack of rows of blocks. So you put another stack on top. Now, though, we have a multi-dimensional array, but they still all have to be characters, or all integers, all floats, all doubles. We cannot mix up the data types, even though there are 2 different rows of data, because what's really happening is that these items are one long contiguous group of bytes in memory. They are strung out one after the other in memory, and we just get to them by calculating the row sizes and adding the final element on the right-hand side, the least most value, to get the offset into the array, into the row. A 3-dimensional array is similar to a Rubik's Cube. And I'm not going to go into all the dimension and all of that it takes to create a 3-dimensional array, but it's going to be very similar to what you're about to see here in a 2-dimensional array. Now here's a single dimension that we've already talked about. We have a little character array called hi. We've left this open so that it will be defined at compile time, and it will be 6 because there's 5 characters here and then our null, because we put the double quotes around it. So this is what comes up in memory, HELLO, and then the null at the end of it. So this is hi sub 0, hi sub 1, 2, 3, 4, and hi sub 5. And the sub goes right into there. That's a single dimension array. Now here's an example of a multi-dimension array and what you have to provide to be able to initialize it this way. This one we'll call greet, and we have an empty dimension here, so that we'll let the compiler calculate that, but we don't rely on the compiler to calculate this value. We have to tell it how long the longest one will be, and then it will set it aside. If you skip that, it will give you an error that it needs a subscript in here, because it's not going to go through these and figure out which one is the longest and set all this up for you. So here is greet 00 is this H, the very first byte of our array. And here's our hello, just like we had before. But these 3 bytes are padded out with nulls, because this thing has to be relatively square. We can't have these odd length values, because then if we did, we couldn't calculate our way through it with using the subscripts times the length of this value, of this length here, which is 8. Yes, which is 8. So we take 1 times 8 plus 0, and add that to the base pointer, and that gets us to this byte, which is the first character of HOLA, sub 1 sub 0, HOLA, and then we pad it out with null so that the math for 2 times 8, 16, plus 0 gets us to this B, and bonjour, and 1 null. That's our longest value. And then chow, we have 3 0, or 3 times 8. We can count off all those numbers, but that 24 added to greet will get us to the address of the C, and then we read until we hit a null, and that's a valid string. 3-dimensional arrays are set up just the same way. You just have another pair of brackets here, a more complicated initializer if you're going to initialize it. You can even have a 4-dimensional array if you want. I wouldn't try to draw a picture of it. You could cause the room to implode, but 2- and 3-dimensional arrays are difficult enough to lay out in memory and in your program. But that's a multi-dimensional array, and it's very simple to subscript your way through it and find values in the array. You would use this for storing intermediate rows in a database. When you pull them in off of the database, you would pull them into an array. That's assuming that all of the values in the row are the same type. Now, that's not likely in a database record, is it? That's when we're going to get into structures, and we'll see structures a few videos down the road here, but just whets your appetite a little bit here. So that's multi-dimensional arrays. Now, at first glance, this probably looks to you just like the multi-dimensional array initialization that we just did in the previous video, but this is not. This is an initialization of a pointer array. Notice that with our static character pointer here, we have a name array, but there's only one dimension to it. This is not really a multi-dimensional array. This is an array of pointers. The pointers will be created off of these static items here. We said that these are static characters, so they are allowed to be put into storage in some place where they will not be changed, and we don't have to worry about them again. This thing will be set up at compile time, and it will be nicely usable, but it will save us storage and execution time because of the way we've built it. Now, this little function, and you can find this in K&R under the same topic here, initialization of pointer arrays. This little function will return a character pointer, char star, right there, month name. So that's telling us that month name returns a character pointer when it returns something, and it will take in an integer n, and that's the number of the month is what we have to pass in here. So here's our static character. Our name array, single dimension, is then initialized by these values. This will be value 0. Illegal month, then value 1, 2, and 3, 4, 5, 6, and so on out to value 12 for December. Makes sense, huh? Now here's our return. Our return is going to use our little decision character that we looked at, our comparison and return operator that we looked at a long time ago. We're going to do a quick check here and find out if n is less than 1 or n is greater than 12. That's an invalid month. And if that happens to be true, we will return this first value, which is name sub 0. And name sub 0 is the pointer. Remember, this is a 13-element array because we have 13 elements here from illegal month through December. It will return the pointer stored in name sub 0. Month name is supposed to return a character pointer, so that's exactly what we have to send back and what we can send back by this. If this is not true, that means that n is in fact between 1 and 12 inclusive, so we will return name sub n which will be 1, 2, 3, 4, 5, 6, and so on down through 12. And this function works the way we expect it to. But I want you to see how you initialize a pointer array, and even though it appears to be a two-dimensional array, it is in fact only a single-dimensional array of pointers. I don't really want to belabor the point, but I want you to see the difference here between pointers and multi-dimensional arrays. Here on the left is the code that we just looked at in the previous video, where we had the month name returned as a pointer. Same thing over here in our new piece of code. But the big difference is, in this side, we have a character array, character pointer array called name, which will have a number of pointers to these static names. Over here, we have a two-dimensional array. We have not set the left subscript. We'll let the compiler figure that out. But we do have to set the right subscript, which is 14. Illegal month is the longest one, 13 characters and a null. Well, what's going to happen here? What's the big difference? In this array of pointers, we have a very small piece of memory set aside here, which is large enough to contain these 13 items, or 13 pointers. So if a pointer is 4 byte, it's 13 times that, 52 characters, or 52 bytes is set aside in here to contain all of these pointers. These values are static characters, and they're off outside of our data area, so they're not taking up data space. Now on this side, we have an unknown array subscript, but we know it'll be 13. But it's going to be times 14 characters each. And I'm not going to do the math. I don't care to. You can if you like. To figure out just how big this block of memory is going to be that's set aside here. Now, of course, it's no big deal in what we're doing here, but if you're doing a large program and you want quick access to the data variables without having to scroll through all of that data to try to find something, and not having a bunch of empty space like we looked at in the previous slide, you want to use the array of pointers. Pointers are your friend rather than multi-dimensional arrays. The major difference is that you can have multiple variable length items in your array of pointers, because we don't really care how big the things are that the pointers point to. It does make a difference to us, though, in a multi-dimensional array where we wind up with a lot of empty space, because all of these have to be the same size, even though they're not really going to fill it up. So in pointers versus multi-dimensional arrays, pointers will win every time. Now we're going to take a look at a real-world use of an array of character pointers. And we've already looked at it a little bit, but let's take a little closer look. This is the argc and argv, the argument count and argument vector array. The argc is the number of command line items that have come into our program from the outside world. We are going to use both of these heavily when we get to a later chapter and we talk about using C programming on the web, because when you submit a request to a website by typing in a URL and providing parameters, those parameters come into your program through the argument vector, and the argument count will tell you how many parameters are on the request line that comes in from the internet. So this will be very important to us later on. We're just going to do a simple little program right now, though, called echo, and the way you would run it is, you can see there, echo hello world would print out hello world. Here's the program. It's pretty simple. We include standard I/O, and here we're going to get our int argc and our character array of pointers, argv, or argument vector is what it's normally called. You, of course, could call these whatever you want, but most C programmers are going to stick with this definition, this standard, and use argc and argv. C doesn't care what you call these, just that there is an integer and a character array, pointer array in that order. While while we decrement the argument count, if that is still greater than 0, then we have something to say. We have something to print. And we're going to print two strings together. One of them will be the contents of the incremented argument vector. So we will increment that pointer. And since it points to a number of string pointers, it will go from one word to the next off of our command line. argv sub 0 is the name of our program itself. Well, we don't want that. We don't care about sub 0. We want the first word, and that is why we do a pre-increment right here. If the argument count is greater than 1, we print a space in this second string. Otherwise, we print an empty character in here just to fill out the %s. And then that's the while just controls the one statement. So that will run through all of our arguments, and then we'll finish off with a new line and exit the program. So let's go take a look at that. Here is echo.c. It's all the same thing we just looked at. Here we'll come to our compile. Compile and link it. Links and compiles just fine. And it prints out every one of our arguments without printing out the name of the program, just the way it's supposed to work. We said echo hello world, this is a test. Hello world, this is a test is every one of our command line parameters, just the way it was supposed to work. It's nice when that happens in a language now and then. Here's an interesting little option. This is a pointer to a function. Now, since any address in memory can be pointed to, and our code obviously takes up memory space, it sits out there in the code segments, we can get a pointer to a function. And then we usually wind up passing those pointers to even to the operating system and to other parts of our program to be called. This is extremely useful for something called a callback hook. Those are used a lot in network security and Linux and other places where you want to give a pointer to your own created function to the operating system. For example, here we're defining a simple function called foo. This is our normal definition, a lot of statements in there. Here we are now going to create something called a void pointer. It doesn't point to a character or an int or anything like that. It's undefined. It's a void pointer. It's defined as not pointing to any of those types because we're not going to increment it or do any math or anything like that. This is the clean way to do it. In old C code, pre-ANSI standard, this would have been a char or a character pointer. Now we call it a void pointer. So here's a void star f pointer, and that's set equal to foo. And since we know that foo is the name of a function declared up here and defined up here, foo is the name or is the address of that function, just like the name of an array is the address of the 0th element. Foo by itself is the address of the first executable byte of this function. So now that's inside f pointer. If we want to call foo by that address, we have to use the parens around star f pointer. Otherwise, we would get the contents of the address, and that's not what we want. We want to make the function call of the piece of code that is sitting inside f pointer. So we cover it in parens to get the order of execution correct, and the parens here would have parameters in them if they were necessary to operate on foo. But that's a callback hook or a pointer to a function. I don't really see that you're going to have a great deal of use for that right now. You've got to get into some pretty advanced C programming before you're going to start throwing around the addresses of functions that you write. Maybe we'll save that for a later video series. But I at least wanted you to see that such a thing as a pointer to a function exists, because if you start digging around in Linux or other advanced code, you will see such a thing, and I want you to have some idea what it is.